So we have seen Prim's algorithm for building a minimum cost spanning tree. The other way of implementing the greedy strategy for building minimum cost spanning trees yields a new algorithm called Kruskals algorithm. So Kruskals algorithm does the following. It enumerates all edges in ascending order of cost. Okay? And now what we do is that we add an edge if it doesn't create a cycle. But there is no assumption that the edges currently chosen form a tree. So they could be disconnected. So in general, what we have at any given time is what is called a forest, okay, which is a collection of disjoint trees. So we don't actually have a tree at any intermediate point, but eventually these forests will combine together, and they will be linked by edges which cross from one tree in the forest to another tree in the forest. And in the end, Kruskals algorithm will actually produce a single tree for us. So let's look at an example to see how this would work. So here we have the same graph on which we initially executed Prim's algorithm. Okay. So we will begin Kruskals algorithm by assuming that the edges are sorted in ascending order. So we'll start with the smallest edge, which is this edge with weight 10. Now Prim's algorithm would try to extend it into a tree by taking an edge which is connected to this existing tree. But in Kruskals algorithm, we don't necessarily need to keep a tree. We will just look at the next smallest edge overall. So we look at this, and that's 12, and it says that 12 doesn't form a cycle with the current edge, so I will include it. So now I have a forest consisting of two trees. I have a tree containing 1 and 6 connected by an edge, and I have another tree containing 3 and 4 connected by an edge, but these are two disjoint trees. So continuing this way, the next edge that I look at is 14, and I add it because it doesn't create a cycle. The next smallest edge is 16. I can add it also, it doesn't create a cycle, and now currently I have 3 disjoint trees in my forest. Adding the edge 16 in fact collapses 2 of them together. So now I come back down to 2 disjoint trees in my forest. Now the next edge which I could consider is 18, but if I add 18, notice that I form a cycle because I have already 3 edges going around this quadrilateral. So I can't add 18, so I skip 18. The next smallest edge is 22. So I look at 22 and I say yes, I can add 22, and I put it in. Now at this point I still have 2 disjoint trees comprising my forest. The next edge is 24, but if I put 24 in, again I will form a cycle involving these 5 nodes, so I can't do 24, so I skip it. Then I come to 25, and at 25 I finally combine the 2 trees in my forest into a single tree, and now I have added n-1 edges, and so I'm done. So if you go back and look at the tree that Prim's algorithm produced, you'll find it's exactly the same tree, and this is not surprising because, as we mentioned earlier, if there are if there are distinct as edge weights, if all the edges in the graph have got different weights, then there is only one unique minimum cost spanning tree, and so any algorithm. So remember that Kruskals algorithm in general has a forest at each intermediate stage. So we can think of singleton vertices which are not connected to anything in the forest as trivial trees. This is like in Prim's algorithm where we started with one vertex. So a tree with one vertex has 0 edges. Okay, so these are trivial trees. So the thing to observe is that this forest is a partition of the vertices into disjoint components. So at any given point, if we look at our graph, okay, as a collection of vertices, then we'll have a forest connecting some parts of this graph, and each forest is disconnected from the remaining, each tree in the forest is disconnected from the remaining things. So each connected part is a connected component. And now what happens when we add an edge in general is that we will take two vertices which are in different components and connect them, and we would therefore end up erasing this boundary and merging these two components to a single component. And in particular, in this component model, we would not add an edge which is within a component, because it will connect two vertices which are already connected. Remember, a component is a connected set of vertices through a tree, so this would add a cycle. So this kind of thing would not be done, right? So we need some data structure to manipulate this, and there is a natural data structure for this, which is this disjoint set. Okay? We have already seen this disjoint set data structure in the context of job scheduling. So what the disjoint set data structure does is it allows us to keep track of these components, so that we have these two operations, find of u, which returns the component containing u, and we have a union operation which allows us to take two components, okay, and it combines these components. So we need to use this data structure in order to keep track of this forest structure that Kruskals algorithm actually builds up. So with this in mind, let's look at the pseudocode for the algorithm. So as in Prim's algorithm, the parameters that we pass to Kruskals algorithm is a set of edges, the cost information, the number of vertices, and T will contain the tree that we are building up. Now the first step that we need to do in Kruskals algorithm is to organize the edges in order of cost. So we could either sort them and put them into a list, or in this particular case we will organize them as a heap, so that at each point we can pick out the smallest cost edge which has not been seen so far. So we construct a min heap H of all the edges, and the heap is organized based on the cost of the edges. Now we initialize for every vertex, we initialize its component to be itself. In other words, each vertex is initially an isolated component consisting of that vertex alone. Initially we don't have a tree at all, so the minimum cost is 0. And now we do the following. So I keeps track of how many edges we have actually added. Now here, remember, when we look at an edge, we may or may not add it. In Prim's algorithm, we always pick up an edge that we will add. So we know in advance that we can do something n-1 times. Here we will have to pick up each edge and decide whether to add it or not. So we keep a track of a counter of how many edges we have added, and we put into a while loop. So while we have added less than n-1 edges, what we do is we first look at the smallest edge that remains in the heap, find the components u and v corresponding to this edges. So if uv is the edge, we find the components j and k corresponding to these edges, right? Now if these are two disjoint components, so j and k are different components, the edge actually connects two different components and it's not going to cause a cycle. So if this j is not equal to k, then we will increment our count, saying we have added one more edge to our tree. We will update the tree itself to have endpoints u and v. We will update the cost by the cost of this new edge, and now we will merge the components. We will take the union of the component j containing u and the k containing v, and we will get one single component which contains all of j and all of k. So we do this until we have added n-1 edges. When we have added n-1 edges, we know that we have constructed a tree, and by the property that we are only adding edges across components, we know that we have added no cycles, and at the end we return the minimum cost. So let's look at the complexity of Kruskals algorithm. So in Kruskals algorithm, the outer loop cycles through all possible edges in the graph. So as usual, let m denote the number of edges. So we have an outer loop that executes m times. Now inside the loop, we do two things. So one is we have to delete the minimum element from the heap H. So since the heap contains all edges, the heap is at most of size m, so this is a log m operation for each deletement. Then we do two finds and possibly one union operation. So we do the union operation only if this particular edge is included in our tree, otherwise we find the two endpoints and we proceed. So in general, across all these m iterations, we have order m operations on this disjoint set data structure. So therefore, order m operations is almost linear in M. So the total cost of all these finds and unions across all the things is just something slightly bigger than order m. So this means that the cost that dominates Kruskal is actually this log m step inside each loop. So overall, Kruskal takes time O m log m. So finally, let us look at the proof that Kruskal's algorithm actually produces a minimum cost spanning tree. Right? So let's assume that Kruskal produces a tree T, right? And there is some other optimal tree T prime. So as usual, we'll show that we can step by step transform T prime to T without sacrificing optimality. So let's assume that this particular tree that we got from Kruskal's algorithm has a set of edges E of T, and the other one has a set of edges E of T prime. So E of T prime is a set of edges in this optimal solution which came from somewhere else, and Kruskal has produced T, and our assumption is that T is not equal to T prime, so the edge sets are different. If they're the same, then there's nothing to prove. Okay? So since they are different, there is some edges in T and not in T prime. So we find Q in T, not in T prime, of minimum cost. Right? So now if we add Q to T prime, we get a cycle. Right? So this cycle, we can draw it. Okay. So we have this edge Q that we have just added, and this forms a cycle with some existing edges E1, E2, E3, E4, and so on. Okay, up to some, possibly some EK. So there's a bunch of edges which are, because I've added Q, which was in T, not in T prime, I added it to T prime. T prime was a tree. You add any edge to a tree, it forms a cycle, and this is the cycle I form. So now what I look at is I look at the cycle. Now notice that because Q is in T and there's no cycle involving Q, at least one of these edges must be in T prime but not in T. So there must be, find some EJ on the cycle that is in T prime but not in T. Okay? So now the claim is that the cost of Q is less than or equal to the cost of EJ. Okay? So EJ is the edge on the cycle which is not in the Kruskal tree. So Q is the edge which I added to the optimal tree because Q was in the Kruskal tree, and created a cycle, and I find a edge on that cycle which is not in the Kruskal tree, and I claim that the edge that is there must be at least as expensive as the edge Q which I've inserted. So suppose cost of EJ is actually strictly less than the cost of Q. Now remember that Q is the smallest edge which is in T and not in T prime. So if we will, first of all, Kruskal will consider EJ before Q, because Kruskal processes the edges in ascending order of cost. At the point when EJ is added, so when EJ is considered, it does not form a cycle. Why? Because all the edges which are smaller than Q, which are there in the Kruskal tree, are also there in T prime. So if EJ formed a cycle in T, it would also form a cycle in T prime, but it is in T prime, and T prime doesn't have any cycles. Okay, so therefore we know that EJ, if it had been considered before Q, could not have formed a cycle, and so the Kruskal's algorithm would have added it. And the fact that it did not add it is a contradiction, right? So therefore this cannot be the case, and we must have the situation that cost of Q is actually less than or equal to cost of EJ. So now what we will do is, therefore we will transform T prime by adding Q and dropping EJ. You can verify that the resulting thing is a new spanning tree. This is not difficult to argue, and we will leave it as an exercise to prove this. What about the cost of T prime? Well, we know that because T prime is optimal, okay, the cost of T double prime must be bigger than or equal to the cost of T prime, because I cannot construct a smaller tree than T prime by the definition of T prime. On the other hand, I know that the cost of Ej is bigger than or equal to the cost of Q. So the edge I have replaced is not any bigger than the edge which I have lost, and therefore this tells us that the cost of T prime is less than or equal to the cost of T double prime is less than or equal to the cost of T prime, because I have taken an edge Ej and I have replaced it by an edge which is at most as big as Ej. Right? So putting these two together, we must have that cost of T prime is equal to cost of T double prime. So the transformed tree must actually have exactly the same cost, and I have reduced the discrepancy between T prime and T, the Kruskal tree, by one edge. So T double prime is closer to T. So in our usual thing, we repeat this transformation till we get a tree identical to the original T that Kruskals algorithm produced. And since each transformation preserves optimality, the final tree in the sequence of transformations is also optimal, and that is equal to the tree that Kruskal has produced, and therefore Kruskals algorithm is in fact optimal. So to summarize, Kruskals algorithm, unlike Prim's algorithm, does not keep track of a tree, it rather builds a forest, and at various points it combines trees across this forest into a single tree. And if we use this disjoint set data structure, then the complexity of Kruskals algorithm is order m log m, where m, as usual, is the number of edges in our graph.